If we're really serious about decarbonizing global industry, we absolutely have to talk about shipping.
Yeah.
It's the big one out on the high seas.
Definitely. We're talking about just enormous energy needs, especially for crossing entire oceans. It's a huge chunk of emissions.
Yeah, the International Maritime Organization, even back in 2012, they pegged it at 2.1% of global greenhouse gas emissions. That's significant.
And the challenge is so different from, passenger cars or trucks. You can't just slap a massive battery on a container ship.
Right, the weight, the space needed for that kind of range.
Exactly. It's just not feasible. A direct electrification is pretty much off the table for these big journeys. So that pushes us towards indirect electrification.
Synthetic fuels.
Synthetic fuels, precisely. And that's where things get interesting and complex.
Okay, so let's really get into this. We focused today's deep dive on a really detailed analysis that tries to map out this path.
Yeah, a specific study.
We're looking at a paper titled Techno-Economic Analysis of a Decarbonized Shipping Sector. Technology Suggestions for a Fleet in 2030 and 2040. Quite a mouthful.
It is. That's our main source for this discussion. And it's really crucial for you, the listener, to know something up front.
What's that?
This is an analysis based on projections, models, right? And the paper itself was published back in 2018.
Okay, so 6 years ago. That's important context. We're looking at predictions from 2018 about what things might look like in 2030 and 2040.
Exactly. It gives us a fascinating window into thinking from that time, projecting forward.
So what was the main goal? What did this 2018 study actually set out to do?
It had a very practical aim. Find the most cost-effective way to decarbonize, specifically the best combination of synthetic fuels and the propulsion tech to use them.
Okay, so fuel choice and engine choice.
Right. They looked at synthetic fuels made using renewable electricity and captured CO2. And on the propulsion side, they compared traditional internal combustion engines, ICEs, with more advanced fuel cells.
All aiming for net zero emissions for the global fleet in those target years, 2030 and 2040.
That was the mission. Find the cheapest path to net zero shipping.
Let's talk fuels then. What options were on the table in this study?
They focused on 4 specific types, all based on renewable electricity, or RE. There was REFT diesel, that's a synthetic diesel.
Okay.
Then RELNG, which is liquefied synthetic natural gas. Also RELH2, that's liquid hydrogen. And finally, RE-MOH, or methanol.
And the key thing linking all of these?
Is that they're designed to be carbon neutral. The idea is you capture CO2 from the atmosphere or maybe from a biogenic source, combine it with hydrogen made from renewables.
Using electrolysis.
Exactly. Using electrolysis powered by wind or solar. So you create this fuel, burn it, release the CO2, but then capture it again to make more fuel. It's a closed loop.
And a side benefit presumably is lower pollution.
A big one. Because they're synthesized, they burn very cleanly. They can meet those really strict IMO rules on things like sulfur oxides, SOx, and particulate matter. No problem there.
Now, before we dig deeper into those 4, I have to ask about ammonia. It gets talked about a lot today for shipping. Was it included here?
That's a really important question for context, and no, it wasn't. Ammonia, while definitely a major focus in current discussions, wasn't part of the analysis in this particular 2018 study.
Okay, good to know.
Yeah.
So they kept the focus tight on those 4 carbon recycling synthetics: diesel, LNG, hydrogen, and methanol.
Correct.
This process, making fuel from electricity, it's called power to X, or PTX, right?
Mm-hmm.
Where does the power come from?
Right, PTX, power to liquid, power to gas. It covers all these synthetic fuel routes. The study modeled using really optimized renewable setups. Think hybrid solar and wind farms.
In places with great resources.
Exactly. They mentioned locations like Argentina or the Maghreb region in North Africa, places with fantastic sun and wind potential.
And did the analysis give any indication of the production costs? Which fuel looked cheapest to make?
It did, and this was one of the maybe slightly surprising findings at the time. RELH2, the liquid hydrogen, came out with the lowest calculated production cost.
Really? Hydrogen is often seen as expensive. How low are we talking?
The projections were pretty aggressive. They estimated 51 euros per megawatt hour in 2030, dropping down to just 46 euros per megawatt hour by 2040.
Wow, okay. That makes it look very appealing from the supply side.
Definitely. But, as you know, the cost to produce the fuel is only one piece of the puzzle. How much it costs to actually use it to move ships is different.
Which brings us to the core metric they used for comparison.
The levelized cost to mobility.
LCOM.
LCOM.
Right. This sounds like one of those crucial figures that tries to capture everything. How does it work?
It's designed to do exactly that. aggregate all the different costs associated with moving cargo into a single number. The unit they used was euros per 1,000 dead weight ton kilometers.
So it tells you, bottom line, what it costs to transport stuff.
Pretty much. And it's essential because just looking at, say, the fuel price per liter or per MWH is really misleading. You need the whole picture.
So what goes into this LSCA calculation? What are the components?
There are 5 main ones they calculated. First is CapEx, capital expenditure. That's the cost of the engines or the fuel cells, plus the fuel tanks.
Okay, buying the hardware.
Second is OpEx, operational expenditure. Maintenance, spare parts, keeping the propulsion system running.
Got it.
Third, and this one is absolutely critical, especially for some of these fuels, the cost of lost cargo space.
Ah, because the fuels take up room that could otherwise hold paying cargo.
Precisely. Some of these synthetic fuels, particularly hydrogen and methanol, are much less energy dense than traditional diesel. You need significantly bigger tanks.
And bigger tanks mean less space for containers or whatever the ship is carrying. That's a direct hit to revenue potential.
A huge factor. Component 4 is, of course, the actual cost of the fuel itself, the production cost we just talked about.
And number 5.
The assumed cost of CO2 emissions. This is key for comparing against the baseline.
How did they handle that? What was the baseline?
The baseline comparison was against using conventional fossil diesel. But crucially, they applied a carbon price to that fossil diesel.
So level the playing field, essentially.
Or rather, to reflect the expected cost of carbon emissions in the future. They assumed 61 euros per ton of CO2 in 2030, and that rose to 75 euros per ton in 2040.
Okay, so a fairly significant carbon price built into the comparison.
Yes, that carbon price on fossil fuel is what really helps the economics of the carbon neutral options start to look competitive in the model.
Right, so they took these 4 fuels, the 2 propulsion types, crunched all 5 LSOM components. What came out on top? What did the study project as the winner?
The conclusion was pretty clear in their analysis: hydrogen fuel cells. Specifically, ReLH2 liquid hydrogen used in a PM fuel cell, a proton exchange membrane fuel cell.
PE-meal fuel cells running on liquid hydrogen. That was the projected winner for both 2030 and 2040.
That's what their LSCM calculations showed, yes. The most cost-effective pathway.
Now that's interesting because PEM fuel cells, they're still seen as a developing technology, especially for these huge marine applications, aren't they? Why did the study see them winning out so decisively?
It really hinges on some quite optimistic, though the paper argued achievable, projections for 2 things: efficiency gains and cost reductions for the fuel cells themselves.
Okay, explain that.
Well, a PEM fuel cell converts hydrogen directly into electricity to power the ship, right? No combustion. The study forecasted significant drops in the manufacturing costs of these fuel cells between the time of writing, 2018, and those future dates.
And the efficiency.
Big improvements projected there, too. They forecast that the average efficiency of PEM fuel cells could reach 57% by 2040.
57%. That's considerably higher than traditional combustion engines.
Way higher. And that high efficiency is incredibly powerful. It means you need less fuel, less of that already relatively cheap liquid hydrogen to travel the same distance.
So the fuel savings from that high efficiency really drive down the LSCM.
Massively. It's so significant, in fact, that the study found something quite remarkable for the 2040 scenario.
Go on.
They found that hydrogen fuel cells were actually getting close to being cost competitive with fossil diesel, even if you didn't apply that 75 euro per ton CO2 cost.
Wow. So almost competitive on pure economics without needing the carbon price push.
Almost. Driven by that combination of potentially cheap hydrogen fuel production and those projected high efficiencies, that's a potential game changer.
It really is. That's the point where the transition could accelerate purely on market forces.
What about the other options they looked at? How did they stack up in 2040 once you do apply that carbon price?
They weren't necessarily that far behind, actually. ReLNG used in a fuel cell and RE-methanol used in an internal combustion engine. Those were generally the next most competitive.
Depending on the ship.
Yeah, the specific ranking could shift a bit depending on the vessel type, container ship versus tanker, for example.
Yep.
But the bigger picture was convergence.
Meaning that many of the different synthetic fuel and propulsion combinations they analyzed were projected to be within, say, 20% of the LCM of fossil diesel, with its carbon costs, by 2040. The gap was closing rapidly across the board in their model.
Okay, so a range of potentially viable options emerging by 2040, but hydrogen PEM fuel cells leading the pack. Let's dig into the risks and sensitivities, though. We know LSM has multiple parts, Which part drives the cost the most?
The sensitivity analysis they ran confirmed what you might expect. Fuel price is the big one. For almost all the systems they looked at, the cost of the fuel itself was the single largest contributor to the overall LSIM.
Makes sense. And the smallest contributor.
Generally, the capital cost of the tank itself, just building the tank, tended to have the smallest impact on the LSIM. But that doesn't mean tanks aren't important.
Right, because of that lost cargo space issue we mentioned earlier.
Exactly. And this brings us back to the unique challenge with ReLH2, the liquid hydrogen. Even though it won on LSIM overall, it has this major drawback.
The space it takes up, it's bulky, even as a liquid.
Extremely bulky. Liquid hydrogen has a very low energy density by volume. So the tanks required are just huge compared to diesel or even LNG.
Do we have a number on how huge? How much space are we talking?
The study gave a specific example. For a typical short-sea shipping vessel using an internal combustion engine, not even the fuel cell running on ReLH2 in the 2030 scenario,
Yeah?
it required 13.3% of the ship's available deadweight tonnage, the DWT, just for the fuel storage.
Wow, over 13% of your potential cargo capacity just gone, wiped out by the fuel tank.
Compare that to REFT diesel, the synthetic diesel, which needed basically 0% extra space compared to fossil diesel. It's a massive difference.
That's a serious economic hit for a shipper. 13% less revenue potential on every trip.
It absolutely is. The fact that liquid hydrogen still came out as the LCOM winner in their analysis despite this penalty really underscores how powerful those projected fuel cost and efficiency advantages were.
But it highlights a critical vulnerability, doesn't it? If tank technology doesn't improve or if shippers just can't accept that level of cargo loss.
Then the economics could shift rapidly. Optimizing LH2 storage onboard ships is clearly a major hurdle.
Let's circle back to ReLNG for a moment. Synthetic natural gas. You said it's made using captured CO2, so it should be carbon neutral. But did the study treat it as perfectly zero carbon?
Not quite. There's a nuance there related to methane. Methane, CH4, is natural gas.
And it's a potent greenhouse gas itself.
Far more potent than CO2, especially in the short term. The study had to account for the risk of unintentional leakage, what's often called methane slip.
Leakage during production, transports, storage, or even incomplete combustion in the engine.
Exactly. They made an assumption in their base case, a 2% unintentional leakage rate for the methane along the chain.
And because methane has such a high global warming potential.
About 25 times the impact of CO2 over a 100-year time frame, which is the standard comparison. That 2% leakage translates into a non-zero greenhouse gas footprint.
So they actually applied a carbon cost to the ReLNG, despite it being made from recycled carbon.
They did, reflecting the climate impact of that leaked methane. It's an important factor for any methane-based fuel, synthetic or otherwise.
How much did that impact its competitiveness, though? Was it a major penalty?
Interestingly, the study found that while the methane leakage cost was real, its overall effect on the LCOM for ReLNG was pretty small. Negligible, really, especially when compared to the much larger carbon cost applied to the fossil diesel baseline.
So, still potentially competitive, but something to watch carefully.
Definitely. Minimizing methane slip is crucial if LNG, synthetic or fossil, is part of the picture.
Okay, let's think about the real-world market. Forget regulations for a second, just on cost. When does fossil fuel start to look unattractive compared to these cleaner options? What kind of oil price makes synthetics competitive?
The analysis gave some thresholds based on their 2040 projections. They found that the very best options, like the LH2 fuel cells, could potentially start competing with fossil fuels if crude oil prices were only around $75 per barrel.
$75?
Yeah.
That's surprisingly low. That's well within recent historical ranges.
It is, but that's for the absolute leading projected technology in 2040. For most of the other synthetic fuel tech combinations they looked at,
Yes.
they needed a higher oil price to become competitive, generally somewhere between 110 and 130 US dollars per barrel. And remember, that's also assuming that €75 per ton carbon price is being applied to the fossil fuel.
Right, so $110, $130 oil plus a carbon tax makes most of these synthetics look good by 2040, according to this 2018 study.
That's the takeaway from their modeling, yes.
We keep coming back to this. ReLH2 PEM fuel cells came out as the winner in this specific analysis. But you also highlighted the technological uncertainty. Fuel cells aren't as mature as combustion engines, especially at this scale.
And that really is the core tension, the biggest caveat perhaps, in relying solely on this study's conclusion.
Explain that tension.
Well, the economic win for ReLH2 PEM FC is based on projections of significant cost drops and efficiency gains for a technology, PEM fuel cells, that is frankly much less proven in harsh, large-scale marine environments compared to the internal combustion engine. ICEs have been used for over a century.
Even compared to other fuel cell types.
Yes, even compared to solid oxide fuel cells, SOFCs, which the study considered for using fuels like synthetic diesel or LNG. PMs for hydrogen were seen as having the best potential, but perhaps starting from a less mature point for this application back in 2018.
So the reliability of the prediction for PMFCs is inherently lower than for, say, using synthetic methanol in a well-understood ICE.
You could argue that yes, there are significant technological hurdles, scaling challenges, reliability questions that need concrete answers for those optimistic 2040 cost and efficiency targets for fuel cells to actually happen. It's a bigger leap of faith.
It sounds like a bet on innovation paying off.
A calculated one, based on engineering trends, but a bet nonetheless.
Still, the potential scale seems vast if the tech does pan out. You mentioned the fuel production potential earlier.
Yes, that was another striking point from the study. They did a rough calculation looking at just one location, Argentina, with its excellent solar and wind resources.
Right.
They found that, theoretically, tapping those resources in Argentina alone could produce enough renewable hydrogen to meet the entire global shipping sector's energy demand, at least based on the recorded demand back in 2012.
Wow. One country potentially fueling the world's fleet.
It shows the sheer scale of renewable energy potential is there. The resource isn't the fundamental bottleneck, and the power-to-X technology to convert that energy into hydrogen is known, even if it needs scaling.
Okay, so let's recap. We've been diving deep into this specific paper from 2018.
That's techno-economic analysis of a decarbonized shipping sector. Technology suggestions for a fleet in 2030 and 2040.
It laid out a potential roadmap based on cost effectiveness measured by ELCOM, pointing towards liquid hydrogen powering PEM fuel cells as the most promising route, despite the significant cargo space penalty.
Driven by projections of cheap renewable hydrogen production and big jumps in fuel cell efficiency.
But with a major caveat that fuel cell technology needs significant development and scale up to meet those projections.
Exactly. The ICE pathways are perhaps more technologically certain, but maybe less economically optimal according to this analysis.
Which leaves us with a final thought, really building on this. If this study is even directionally correct, and the cost of making renewable liquid hydrogen can become very low, and the fuel cell tech does get efficient.
Then the economics on board the ship start looking really good.
Right. So if the fuel gets cheap and the engine gets efficient, what becomes the real bottleneck? Here's the question we leave you with. How quickly will the massive global challenge of building the infrastructure, the liquefaction plants, the specialized bunker ships, the port facilities for liquid hydrogen become the single greatest barrier preventing the maritime world from actually achieving these potentially low costs?